Okay, so thanks to Ryan for the great talk on the large multimodal models. And in the last part of our tutorial, I'll be covering a very recent research topic, multimodal agents. Here is the overall structure of our tutorial again. And in this part, we answer the fifth question we brought up in the very beginning: how to train multimodal experts with large language model to enable multimodal agents. So first, let's revisit the evolution of modeling paradigm, especially in today's deep learning era. We started with training task-specific models and on small-scale, well-annotated data. And this leads to dedicated models for each task or even each data set. Then, for early foundation models, the pre-train and fine-tune paradigm can take advantage of large-scale, well-crawled, noisy data for pre-training. But the fine-tuning stage is still mostly task-specific on the same small-scale, well-annotated data as the task-specific modeling. And this paradigm has become very popular in both NLP and vision language research. And we witnessed many well-known models, which used to be considered as large-scale models, but maybe more intermediate or even small size in today's view. And nowadays, we are entering a new era of generalist modeling, where the pre-training is done on extra large data. And for downstream adaptation, in-context few shot with a few demonstration examples or zero shot can do the job. We call these models large language or large multimodal models, including the GPT family, PaLM, PaLM-E, Llama, Flamingo, and so on. And going back to the instruction tuning covered by Chunyuan just now, the pipeline of building instruction following models can be still considered as a pre-trained and fine-tuned paradigm. So for example, for Alpaca, it is built on top of the pre-trained Llama and then tuned on instruction tuning dataset. Similarly, for VR models like Lava, an additional stage of image text alignment pre-training is introduced to align the visual representations to the frozen large language model, and then perform instruction tuning. So taking the advantages of large language models, researchers are now exploring a new paradigm that shifts from standalone models for solving finite predefined problems to synergistically training multiple tools or experts to solve complicated open problems. Note that this system can be built without any training involved. So just by taking the advantage of the power of large language models, giving it a few demonstration examples to teach it to generate proper calling of tools. The user will directly interact with the large language model, and based on the user intent, the large language model will plan on what tools to use and in what order. The tools can be open source models, public or private APIs, code interpreters, and the output from all these tools will be feedback to the large language model in text and summarized by it to as the response to the user. And this new paradigm has been previously studied in NLP to train specialized NLP tools to solve more complicated problems. For example, the NLP tools can be calculator, calendar, search engine, or specialized models for question answering and machine translation. And as shown in the table here, all those methods, they don't have image understanding capabilities. And inspired by the previous NLP text-only agents, just in the span of 3 months, we are seeing many works proposed to build multimodal agents to explore whether we can use large language models to train multimodal experts for more complicated multimodal understanding problems. And the multimodal agents displayed in this slide is just a glimpse into the fast evolution along this direction. And in this talk, we'll use MMReact as an example to show how we can train multimodal experts with large language model for advanced multimodal reasoning and action. MMReact leverages ChatGPT as the large language model, with chat as the user interaction interface, and can support both inputs and outputs in multiple modalities, including text, image, and video. In its design, it composes numerous vision experts with ChatGPT. And ChatGPT is the tool allocator, plans on which tools to use and in what order based on the input image and the user intent. The user intent can be a question like the one showing here. How many championship rings did the player on the left win in his career? And the next will show a breakdown of the planning and execution steps behind the scene and explain in detail how MMReact works. As ChatGPT only accepts language inputs, to enable image as input to ChatGPT, we simply use the file path as the input. The file path will function as a placeholder, allowing ChatGPT to treat it as a black box. So upon receiving this file path, ChatGPT will recognize, oh, it stands for image input. And next, to grasp a general understanding about the image, ChatGPT plans on what tool to use. For example, image captioning for an overall description of the image, dense captioning to get a reasonable, more detailed description about each object in the image, object tagging to get the object tags, and as the tags may mention faces, it further invokes face detection to get the bounding box coordinates of the two faces. And face detections may localize the faces in the image, but it doesn't recognize the identities of these faces. So celebrity recognition is called to get the names of these two persons. For each call, the outputs from the tool are serialized in text and feedback to ChatGPT for it to decide the next move. And when ChatGPT decides no external experts are needed, it takes the observation gathered from the calling of all the tools, a total of 5 showing here, and summarize it as the response to the user. Now, if the user asks, how many championship rings did the player on the left win in his career? It's not in the observation, but ChatGPT has the knowledge of the bounding boxes to decide who is on the left, and also the names of the player. It can take that information and invoke Bing search to find the right answer, which should be 5. So with the help of all these external experts, MMReact enables ChatGPT with more advanced capabilities for multimodal reasoning and action. For example, visual math and the text reasoning to solve math equations in the input image, understanding visual condition joke or memes, understanding spatial relationships between objects in the image or the bounding box coordinates, visual planning and prediction, reasoning over multiple image inputs, multi-hop document understanding, open word concept understanding, for example, product brands, celebrity, and food, video summarization, or event localization. And we will be showing 3 examples to let you have a close look into the advanced capabilities of MMReact. So the first one is for multi-image reasoning. Imagine that you are a very organized person. You take a photo of the receipt whenever you make a purchase. MMReact can reason over multiple receipts and summarize your spendings. So in the example we're showing here, we upload 4 receipts one at a time. Each time when the MMReact receives the receipt, it first recognizes the text in the receipt image and summarizes the spendings shown in the current receipt image. After all 4 receipts are uploaded, we first ask a few simple questions with only one receipt involved. For example, how much did I spend on grocery? MMReact can correctly identify that the grocery spending is associated with the 3rd receipt image and return the total amount from that receipt as the answer. And similarly, for the second question, only the last receipt is needed to answer the question. Then we try a level up by asking how much did I spend on travel? MMReact correctly identifies the flight ticket and the Uber ride should be categorized as travel and return the summation of the spendings on the first 2 receipts. And finally, we ask how much did I spend on paying taxes? MMReact successfully finds the amount of tax I paid from all the receipts. Note that for the grocery one, there is no tax shown. So a total of 3 tax items here. And the second scenario is for multi-round image editing. When equipped with image editing tools, MMReact can enable dialogue-based image editing. Here we borrow the image of a squirrel holding a camera shown in the GPT-4 demo. We added one object in the image at a time. The edited images show a desired change from the previous input images while keeping the remaining part intact. And finally, we show how MMReact can perform video analysis. We first upload a video of Kobe's last amazing 3 minutes in his NBA final game. The whole video is about 7 minutes long. And MMReact first returns a detailed summary about the video. We then ask a grounding question. How did Kobe win the last 2 points to get 60? Explain and provide me with a short video highlight. The first half of the question, it only requires the system to explain it verbally, while for the second half, it requires temporal grounding to provide the exact start and end time when the 2 free throws happen. As you can see, the returned video highlight indeed captures the 2 free throws from Kobe. So, okay, with MMReact as an example, we now have a basic understanding of how a multimodal agent works. Next, I'll cover the unique benefit of this new paradigm from 2 perspectives: extensibility of the large language model, the core part of the system, and extensibility of the tools. So the large language model in the system can be upgraded to a newer, more powerful model when it comes out with no sweat. We tested by upgrading ChatGPT in MMReact to language-only GPT-4. And we use 2 testing examples from the GPT-4 demo. The first one is solving the physics problem from a textbook image. And with ChatGPT, we see that it returns vague problem-solving steps with no concrete answer. And if we upgrade the ChatGPT to language-only GPT-4, we can get exact same correct answer as the multimodal GPT-4. And another example is the coding with vision inputs from a rough sketch of the joke website shown in the multimodal GPT-4 demo. We tried this on Emergent with both ChatGPT and language-only GPT-4. Both can generate runnable code to build that website. But while for the one with ChatGPT, it has less style formatting than the one with language-only GPT-4. And another observation that is hard to show here in the slide is that the button to reveal punchline is not actually working with the one from ChatGPT. And we should all believe that GPT-4 is not the ending for developing large language model. And we can always replace the large language model in this system with a stronger and more powerful model when available. And with SAM as the popular vision foundation model, so to speak, one can combine it with GPT to allow for more types of human interaction with multimodal agents other than the text. Recall that in Emergent, the user intent is all captured by the language, natural language inputs from the user. In intern GPT, by connecting the tool SAM with GPT, it allows for more ways to interact with the system. For example, via clicks, scribbles, and drawing bounding boxes. All these interactions are similar to human finger pointing when us humans are having a conversation. And SAM may be one powerful tool to add. In general, the design of existing multimodal agents incorporates tool via a plug and play mechanism, allowing for adding even more tools. So for example, Hugging GPT is proposed to leverage all open source models from Hugging Face. And Chameleon incorporates not only Hugging Face models, but open source models from GitHub, plus Bing Search API, plus Python compiler. As a grand vision, task matrix.ai envisions that large language model or multimodal large language model can serve as the allocator to connect even millions of APIs and may enable even advanced applications such as office automation, AI of things, robotics, or AI copilots. There are also works on improving this new paradigm, mostly focused on the planning step. The previously mentioned multimodal agents all uses natural language to prompt a large language model for planning and to decide which tools to use. One can use programming language for more accurate execution. However, as the codes are still generated by a large language model, the problem of inaccurate tool using still remains. And a recent work, Assist GPT, tried to improve the accuracy in tool using via self-assessment. It adds a stage of inspection and learning into the system. And when the round of plan and execution is finished, the system inspects the outcome and determines whether the reasoning path of calling an API is a success or not. If so, it will automatically add this example as an in-context example to teach large language model to for more accurate tool calling in the future rounds. And another thread on improving accuracy in tool using is to combine the system with instruction tuning. One can generate a data set of instruction API pairs via self-instruct to tune a smaller large language model. And by composing tools from a more specific domain, this new system paradigm can also support diverse domain-specific applications. So like what have been mentioned by Zhenyuan in his part, we can compose image synthesis tools with object level, pixel level, or image level understanding tools, and have a data synthesis pipeline to provide diverse annotations on synthesized images. And when composing the large language model with robotic executors, one can enable robotic actions based on multimodal instructions. And when training a pool of audio models with large language model, audio GPT can understand and generate speech, music, sound, and talking heads. And with tracking, captioning, audio understanding models, chat video enables ChatGPT to understand multi-channel videos. And finally, we envision future directions on this new paradigm, suggesting what more we can do to further improve the current system. For one, imagine if we have a completely new scenario without a robust tool to use. Can we create a tool based on the user need on the fly? In NLP, creator has explored to create tools for math reasoning by writing Python code. Instead of calling off-the-shelf math solver API like Wolfram Alpha. So in terms of multimodal agents, can we create tools that can process multimodal inputs? For example, leveraging pre-existent Python packages such as OpenCV. Or even one day, can we build a deep learning tool on the fly? And the second direction is retrieval-augmented multimodal agents. This is inspired by retrieval-augmented large language model. For instance, if we have a database with a product image and the price pairs, can a multimodal agent retrieve the corresponding price given when prompted with the a product image? And the third direction is for evaluation. Although we have seen successes in building multimodal agents, mostly by example demonstration in the paper. And can we have a systematic way to evaluate how accurate it is for this type of system to use multimodal tools? API Bank is a starting point to building such pipeline in evaluating tool-augmented large language models. And finally, still on the evaluation side, perhaps also relevant to the large multimodal model covered by Chunyuan just now, there are a few works already exploring this to evaluate the emergent capabilities of large multimodal models and multimodal agents. But this emergent capabilities, there are probably more to come. And also they are not either covered by existing benchmarks, or the long chatty output from these models are not suitable for today's evaluation metrics. And we may need to think about new ways or new benchmarks to evaluate these emergent capabilities. And as a summary, from the last two talks of today's tutorial, we have covered two directions on building advanced multimodal systems, all based on large language model. One is instruction tuning from the last talk, and the other is the tool using in this talk. These two directions have their own pros and cons. For one, that instruction tuning can enable an end-to-end model that directly interprets rich semantics in multimodal inputs. However, as it requires training, it requires data curation and computation resources, hence much more expensive. And when tuned with limited data, it will lead to limited capabilities in certain scenarios, like OCR mentioned by Chunyuan. And for the other hand, for tool using, there's no training needed. We can leverage off-the-shelf abundant models, APIs, or code interpreters as the tool. However, as it doesn't require training, we see failures in invoking the right tool with the system. And also, if we train large language model with weak domain experts, we see weak performances. And in addition, I want to bring up two more in-depth research questions. As we now have open source large multimodal models like Lava, can we replace the large language model in the system with Lava as the tool allocator? If so, what is the criteria to decide which capabilities can be solved by instruction tuning, and what other capabilities that require a tool to build such advanced system. And with this slide, I would like to conclude today's tutorial with a recap on all the content we have covered today. We started with the focus on image encoder that consumes visual data and discussed how to learn image representations via visual pre-training and vision language pre-training, and how to extend vision models with more flexible, promptable interface to build a unified vision interface. We then covered image generation that produces visual data with a focus on alignment. And finally, we made connections to large language models to build a general purpose interface from two perspectives: one to train large multimodal models, and the other to train multimodal experts with large language model to enable multimodal agents.